As a third topic of today, I will discuss about general stress state in 3D and stress transformation in 3D. As I told you, it is like out of scope of ME231 if we discuss about all general, stress state in 3D. We'll focus on rather special cases in 3D because it's necessary. Okay. Before talking about that special case, let me give you overview. So first of all, let me set up some sort of coordinate system and some vectors and angles, and based on that, let me do something similar that we did back in Mohr circle and plane stress problem. So here, what you're gonna do is following. In out of x, y, z coordinate, we'll take a vector n, and to this vector n, we can define three angles from x-axis, y-axis, and z-axis: theta g, theta y, theta z. Okay, and we're gonna call directional cosine as lambda x, cosine theta x, lambda y, cosine theta y, lambda g, and cosine theta g. After defining this vector n, we can define a plane that is orthogonal to this n vector, so that you can consider this n as a surface normal vector to some sort of inclined surface. So here, after taking a plane that is orthogonal to this vector n, and what you're gonna do is we'll take triangle, using the intersection between y, x, and z axis. Okay, then what you can imagine here is we have this plane, we have that triangle plane, we also have the bottom triangle surface, and finally we have this inclined surface. We have four surfaces. So if you recall, in Mohr circle for plane stress problem, we take out these two-dimensional triangle and try to consider the transformation between sigma x prime, sigma x, and sigma y, and tau x prime, y prime, and tau xy by setting up these kind of triangle. We can do a 3D version of this thing, and actually I'm not gonna follow all the derivation in textbook. Actually, in textbook, what you can find is it is shown that normal stress on this inclined surface that is perpendicular to n vector can be written as like a function of sigma x, sigma y, sigma z, tau xy, tau yz, and tau xz, and we have some directional cosines. Okay. So why do we have directional cosine scales? Because this is a stress is the tensor quantity, and you have to have cosine factor when you define the area. You have a cosine factor when you take the projection of forces. Okay, that's why we have cosine something multiplied by cosine when you obtain the stress transformation. Here, what you have to notice is that it is a so-called quadratic form. Okay, so you're gonna learn about quadratic form in linear algebra class, but what you're gonna realize and what you're gonna learn in linear algebra is that for any quadratic form, it can be shown that we are guaranteed to find lambda x prime, lambda y prime, lambda g prime, or equivalently x prime, y prime, g prime coordinate, such that sigma n prime equals to be sigma x prime, lambda x prime squared, and this second term and third term with all tau x prime, y prime, and other tau component to be 0. Okay, it is a so-called principal axis because there is no shear stress component, and sigma x prime and sigma y prime, sigma g prime, these three numbers are principal stresses. Okay, so what you can realize here is that whatever complex stress state you have in three-dimensional problem, you are always guaranteed to find the three principal axes. Of course, you can find that three principal axes if you know the concept of eigenvector and diagonalization. However, because we haven't, I think more than half of you haven't learned about linear algebra and you don't know what is the eigenvector and what is diagonalization. Yeah, we'll skip here, and we'll only consider like special cases I told you. So can we have a more circle in 3D? Yes, there is some special way to memorize three-dimensional stress state transformation. However, it's out of scope of ME tutorial. Yeah, but I can just tell you just to some outcome of this 3D Moore circle. What you're gonna see here is that after finding three principal stress, sigma P1, sigma P2, and sigma P3, you can define three circles. First circle, second circle, and third circle. Okay, and here the meaning of the circle is quite clear. When you consider suppose that this is sigma x prime, suppose that this is sigma y prime, suppose that this is sigma z prime, the first circle, this circle, which pass sigma x prime and sigma y prime, this is like a rotation about g prime axis. When you have a circle that passes through y prime and z prime, it is a rotation about x prime axis. When you have a circle that passes through sigma x prime, sigma z prime, this is then rotation about y prime axis. And other rotations and other coordinate transformation, you can have a sigma and tau value that is located in this shaded region. Okay, so that's the meaning of this Moore circle. Of course, it's really complex to find the sigma, 3 sigma and 3 tau value that is hidden in this graded region, so we'll skip the discussion there. But what you have to remember is once you find three principal stress, you can complete the 3D Moore circle, even though we're not gonna learn how to use this shaded region. But what you can realize is there is three principal stress, and the maximum shear stress can be different from the maximum stress you found from principal stress. Okay, so possibly you may work on this region, you may work on this region. If then 2D Moore circle does not give you full information, only after completing the 3D Moore circle you can have a complete information on maximum shear stress. Okay, so let's solve one example problem which would give you better and deeper understanding. So for XYZ axis, six stress components are given as this. Sigma x is 40 megapascal, sigma y is 25 megapascal, and tau xy is given as negative 20 megapascal, and all other components including g axis is 0, so that you can see that this is a plane stress problem. Then somebody asks, what is principal axis and stress in 3D plane? What is maximum shear stress in first 3D? Okay, so until now we only consider coordinate transform with the g-axis fixed or rotation of xy with respect to z-axis. However, actually, maximum shear stress in 3D can occur in completely different plane, and let's see if it's the case. So first, let's solve the plane stress problem. So please remember that we already know the one principal stress, which is sigma z is 0, and our job is try to find the plane stress in two other principal stress. We already know one principal stress, so let's define x out of this and y out of this, and let's also obtain sigma average, which is average of 40 and 25. Okay, so which is 32.5, and we have tau xy is negative 20. So if you do negative 20, it's 20. You plug in negative 20, it becomes like this. And the radius of Moore circle after plugging in our numbers, it's 21.4 megapascal. So based on that, let's try to complete the 2D Moore circle. So we have our x, which is 40 and 20. we have our y, which is 25 and negative 40, no, negative 20. And we have our origin at 32.5 and 0 position. And, radius is given as 21.4 megapascal. So after making 2 theta clockwise rotation, you can find the location x prime 53.9 and 0. You do 32.5 plus 21.4. And regarding x prime, you do 32.5 minus 21.4, which is 11.1. So you found this and this two principal stress, and at this axis you have 0 x prime, tau x prime, y prime. Okay, so what you can realize is we already have the tau in shear stress, including the g component, is 0, and we now have this guy is 0, and we already know that sigma z is 0, and we consider the rotation about g-axis, and at that specific coordinate system x prime, y prime, we have 11.1 and 53.9 and 0, 3 principal stresses. So after realizing 11.1 and 53.9, this is sigma y prime, this is sigma x prime, this is sigma z. After defining 3 principal axes and 3 principal stress values, we can complete 3D Mohr circle. So if we only consider our typical 2D Mohr circle and the maximum shear strain along this plane, your answer would be this point, right? 21.4 as the maximum shear stress. However, after completing our 3D Mohr circle, you can see that tau max would occur at 26.9 megapascal, which is different from our previous answer. So if the problem asks you try to find the maximum shear stress in full three-dimensional space, you have to always complete Mohr circle by searching for 3 principal stress value. Of course, it's quite hard to solve general stress state problem without the help of linear algebra. So the focus of our study will be only on plane stress problem, so that you only have you are always guaranteed to have one principal stress value is 0. Okay, so here after solving the maximum shear stress, you can see that it's not occurring in xy plane. So let's think about the meaning. As I told you, this is like a sigma z here, sigma x prime here. So what you can realize is this circle is rotation about y prime axis. Okay, so this circle corresponds to rotation about y prime axis. Okay, so that you can think about rotation in this way. Now let's consider this second one, this guy, which passes through sigma x prime, sigma y prime. This is as you know, rotation about g-axis. So if you rotate about g-axis like this, then you can see how the stress state changes. Now we have one more axis to go. If you consider this big circle which passed through sigma z and sigma y prime, then it's rotation about x prime axis. So rotation about x prime axis, you rotate keeping the x prime axis and rotate y prime and g like this, and as you rotate this, you're gonna find a plane with maximum shear stress of 26.9, which is gonna be located at 45-degree angle between g axis and y prime axis. Okay, so this is the geographic visual it's like a visual representation of Mohr circle and general stress transformation. And as I told you, of course we can obtain the principal stress for any stress state. We are always guaranteed to find the principal stress and principal axis. However, we don't have enough knowledge in linear algebra. We'll focus on plane stress problem. Okay. So with that, yeah, you might have some clue on how we can utilize the 3D Moore circle. Without using 3D Moore circle, you're not gonna uh, predict the maximum shear stress correctly. If you don't predict maximum shear stress correctly, you're not gonna correctly define whether the structure is reliable or not, and it'll cause a huge fail. Okay, so how important it is, and we'll discuss about a a very important class of problem considering plane stress. It is called like a thin vessel problem and thin walled vessel problem, and we'll focus on and we'll discuss about the problem in next lecture. Okay.